Hello again. So this is going to be question 7 of the fall 2016 final, and it's going to be covering a question on asymptotics. So the question says that in the following, assume that const is a constant time function call. And also when giving bounds, we want to give bounds that are as tight as possible and as simple as possible. And so let's start with part A. So part A says like we want to give the best and worst case bound on a function of n, and that function is specified here, which is foo1. So let's see what foo1 does. Right? We'll pass in a parameter n to foo1. And so foo1 is going to have a base case. So if n is equal to 0, we want to return. Otherwise, it performs some amount of work in this for loop, and we'll get to that amount of work in just a little bit. And then it's going to make a recursive call. And so this recursive call is going to be calling itself on the input n minus 1. Right. And so now let's actually try to analyze the runtime. Right. So whenever we are faced with a asymptotics question and it's recursive, we can follow this 4-step process. Right? So the first step is going to be draw out recursive call tree. And so what does this mean? This means that for every single recursive call we make, we want a single node in the tree, and we're going to draw directed edges representing which function call is making what call to other function. Right, and so let's take a look at how we do it for foo1. Well, we start out with a function call to, let's say, input n. This is going to be foo1 called on input n. And so what function call does this make? Well, it doesn't hit the base case just yet. It's going to perform some amount of work and then make a recursive call to n minus 1. So the next node is going to be a call to foo1 of n minus 1. Continuing on, we're going to make, we can follow the same like logic and say that it's not going to hit the base case. It's going to perform some amount of work, and then it's going to make a recursive call to n minus 1 again, right? But n here is different from the n we specified right here, right? We're saying that this n is the initial input we give to foo1, whereas this n is just the input to the function that we're looking at, right? So if the input is n minus 1, then this n minus 1 is going to evaluate to this n minus 2, which I know is a little confusing, but make sure you're separating like which n specifies what. And so this is going to be a call to foo1 of n minus 2, where n specifies like this initial input that we give the function. You might imagine that this continues on for quite a bit until we hit our base case. And so this is what the recursive call tree looks like for this part A. And so we can move on to the next step, which is calculating the work per node. And so what is the work per node? Right, that's going to be looking at this part of the code right here. And what happens in that code? We have a for loop that initializes our value of I equal to n. And then it's going to divide I by 2 repeatedly until I is not greater than or equal to 1. Right, so what this means is that if our function, or if our for loop is performing a constant work per iteration, then the amount of work is approximately just the number of iterations that we have. Right? And so how many iterations do we have in this amount of work here? You might recognize this to be a logarithmic number of iterations, but let's see why. Right? And so to do that, let's just take a look at how many iterations we're making. Okay, let's say that we start with iteration 0. So iteration 0 has I equal to n. Iteration 1 is going to have I is equal to n over 2. Iteration 2 is going to have I is equal to n over 4, and so on, right? Until some kth iteration where I is equal to 1, and that's going to be the last iteration. And so in this case, how many iterations do we have here? Well, we just need to solve for k, right? Because that's approximately the number of iterations we have. And to solve for k, we can write, we can see how many times we have to divide by 2 in order to get to 1. Right? And so at the kth iteration, we have n divided by 2k times, right? And we can write this as n divided by 2 to the k. And so if we want its value to be equal to 1, then we can solve for k by multiplying by 2 to the k on both sides. We get that n is equal to 2 to the k, and that k is equal to log of n. right? And so this means that if we have some input n to our function, then it's going to perform log of n amount of work. Right? If we had n minus 1 pass into the function, then it would perform log of n minus 1 amount of work, right? Because n here is the input to this function. And so now let's fill in each of our nodes. Right? I usually like to fill them in just like placing this amount of work within each of the nodes. And so this call will have log n amount of work. This call will have log n minus 1 amount of work, log of n minus 2 amount of work, and so on. And so that completes our second step. And so we can go to our third step. And so the third step is going to be calculating the work per level, right? So levels here refer to just levels in our call tree like this. And we want to calculate the work per level, right? So in this case, the work per level is pretty simple because there's only one node for every level of our call tree. And so the work per level should just be the same as the work per that single node. And so this is over here, and I'll place the work per level on the side. Right, what is the work per level for all of these function calls? This will be log n. This will be log of n minus 1, log of n minus 2, and so on, all the way until we hit our base case. And so now we finished step 3 and we can go on to step 4. So step 4 is going to be computing the total work. And this is sum of work per levels. Right, so basically, you see this column here, we're just going to sum all the way down. And that's going to be the total amount of work we do. And we can use that to approximate the runtime. And so in this case, what is this sum going to look like? This sum is going to be log of n plus log of n minus 1 plus log of n minus 2 plus all the way to log of 1, right? Because that's what we saw as our last value. And so in this case, this sum is going to approximate the runtime. And so what does this sum evaluate to? Here, we can actually apply one of our log rules, right? We said that with logs, if we have log of some value a plus log of some value b, this is equal to log of a times b. And so if we apply that here, we'll see that this entire sum can be written as log of n times n minus 1 times n minus 2 times all the way to 1. And so in this case, what does this look like? Well, another way of writing this is that this is log of n factorial. Cool. And so we aren't done just yet, right? Because we know that we saw in the sorting unit that log of n factorial is actually equal to another form that we've seen more often when looking at asymptotics, right? And we said that log of n factorial is equal to n log n. And so I won't go through this super in depth because it's probably in one of the lectures and I feel like it's going to take too long to go through it here. But we said that log of n factorial must be equal to n log n when looking at comparison sorts and kind of like a lower bound to the best runtime a comparison sort can have. And so in this case, we can write our runtime as being theta of n log n. And so something that the question asked us was to find the best and worst case bounds as a function of n, right? And within our analysis, we never really specify like any difference between like the value of n we choose, whether it's best or worst case, because we're considering an arbitrary n. So this means that for every single possible value of n, as n grows asymptotically larger, then the runtime will still be theta of n log n, right? So basically what I'm trying to say is that in this case, the best and worst case runtimes are the exact same. And so we calculated the work here. We approximated its runtime as theta of n log n. And so that's going to be the best and worst case runtime as well. N log n and also n log n. And so that was part A. As a recap, we followed this 4-step process to calculate the total amount of work done. And then we approximated that total amount of work using this derivation here. All right, so now let's take a look at question B. And so in this case, we once again want to find the best and worst case runtime bounds. But for this question, we're going to be looking at foo2, which takes in 2 inputs. Right, so these 2 inputs are going to be I and n. And so what happens during this method? In this case, this should look pretty familiar where we have a base case. We perform some amount of work. But our recursive calls look a little different, right? Our recursive call, if I is greater than n over 2, is going to be just a single recursive call to I minus 1 comma n. Otherwise, it's going to be a recursive call or 2 recursive calls to I divided by 2 and n. And so something I should note is that in the base case, there was a typo on the exam. And so this should be I instead of n. Otherwise, we never reach the base case. But once again, you should still see this base case work and then recursive calls structure, which we saw in the previous problem. And so this is going to be recursive once again. So we can still use our 4-step process, which I've copied over here. And so let's start by drawing out the recursive tree, right? We'll start once again with a single node at the very top. It makes a call to foo2 of n comma n. And that comes from this part here. And so the base case won't be hit. It'll do some amount of work. And which of the recursive call cases will it be? We're assuming n is pretty large here. And so I is going to be n, which is greater than n over 2. And so we're only going to have one recursive call. And it's going to be going to foo2 of n minus 1 comma n. Now let's repeat this analysis for these set of inputs, right? N minus 1 is not 0. So we're not going to hit our base case. We're going to perform some amount of work, which we'll talk about in a bit. And n minus 1 for really large n is still probably bigger than n over 2. Right? And so we're once again going to go into this base case, or this recursive call case. And so we have a single recursive call made to foo2 of n minus 2 comma n, right? Because we're subtracting 1 from this input here. And remember, once again, make sure to distinguish between what we mean by this n as compared to this n. Right. And so you can imagine that this goes on for some amount of time. And so when is the last time that we make a single recursive call, right? When's the last time that we're in this case? Well, that's going to be when I is just bigger than n over 2. And so put that here as foo2 of n over 2 plus 1. Right. Otherwise, we would not pass this if condition and go to the else case. And so in this case, we still make a single recursive call. It's going to be to foo2 of n over 2 comma n. And now this is when things start changing. I'm running out of space here, so let me shrink this a little bit. Right. And so how are things changing, right? When we make a call to foo2 with parameters n over 2 and n, what's going to happen? We don't hit the base case just yet. We still perform some amount of work, except now this if condition is not true. And so we go to the else case. And what happens in the else case, we're making 2 recursive calls where our inputs are, in this case, I divided by 2, comma n. And so when we look at I equals to n over 2, this means that our recursive calls will look like this. We make 2 recursive calls. And what is the inputs? is going to be n over 4, right? It's going to be n over 2 divided by 2, comma n. And so just to keep things a little bit cleaner, I'll only do one of these per level. And you should just know that this is the same. Now what happens when we have inputs n over 4 comma n? We still haven't hit the base case. We still perform this amount of work, but we're still not passing this if condition also. And so we still make 2 recursive calls. So these recursive calls can be drawn like this. And these calls will be to foo2 of n over 8 comma n. And so you can imagine that at this point and from this point onward until we hit the base case, this branching factor of 2 is going to continue, and our input I is going to continually divide by 2 until we hit the base case. And so at this point, we finished part 1 of our 4-step process, and we've drawn out the recursive call tree, right? A little more difficult than the previous problem, but just following our analysis, we were able to figure it out. And so now let's go on to the second step, which is calculating the work per node. Right? In the work per node, we just look at what happens in this case here. And so what happens in this case? Well, we have a single for loop where update continually increments j. J starts at 0 and ends when j is equal to I. And so the number of iterations we have is going to be equal to I. Each iteration performs constant amount of work, so we can approximate our work to be approximately equal to I. And so I is the first input that we pass into the recursive call. And so let's fill in each of our nodes. Right, in this case, our input is right here. So for each of them, it's just going to be the value that's right there. So we have n minus 1, n minus 2, n over 2 plus 1, n over 2, and then these would both have n over 4. And these would all have n over 8. All right. And so now let's actually try to calculate the work per level. So remember, the work per level is just summing across each of our levels here. And so for most of them, it'll look kind of similar to the previous part, except these bottom couple. And so what does this look like? Our work per level is going to be n here, n minus 1 here, n minus 2, n over 2 plus 1, and then n over 2. And this is when things start to change, right? And so here, our work per level is going to be n over 4 plus n over 4, because each of our 2 nodes has n over 4 amount of work. And so if we sum those up, this should also be n over 2. Likewise, if we sum up this entire level, right, it's going to be n over 8 plus n over 8 plus n over 8 plus n over 8. And so that's going to be n over 2. And so this continues on until the base case. And so as you can see, we can now move on to our 4th step, where we sum over every one of these work per levels. And so our sum is going to look like this, which is n plus n minus 1 plus n minus 2 plus all the way to n over 2 plus 1 plus n over 2. And then from here on out, we sum n over 2s until we hit the base case. And we'll look at like how many n over 2s we have in just a little bit. And so how do we calculate this sum? It looks a bit scary at first, but let's calculate it based on our if conditions, right? So we have one if condition where I is greater than n over 2, right? So this would correspond to this section of our sum here. And then we have the rest over here. And so let's start with the first part. This is going to be an arithmetic sum where n continually is subtracted by 1 all the way until n over 2 plus 1. But we know that we can calculate the sum of an arithmetic sum of an arithmetic series as the first element, so n, plus the last one, n over 2 plus 1, and average those, and then multiply by the number of elements we have, right? So in this case, we're going from n all the way down to n over 2 plus 1. And so there's going to be n over 2 elements here. And so if we write out this sum, we should see that it's around 3n over 4 plus 1/2 times n over 2. With asymptotics, we can calculate the exact value, but it's not super important, right? Because asymptotics are just an approximation anyways. But we see that we have a factor of n here and a factor of n here. And so the amount of work being done in this section is around theta of n squared. Cool. So now we've calculated this part. And so now let's move on to the left or the right hand part. So in this case, we're summing n over 2 a lot of times. So how many times are we summing it? Right. In this case, we know that we're going to, at each level, divide by 2 until we hit the base case, which is when I is equal to 0. And so how many times or how many levels do we have starting from this point onwards? Right. Well, we saw in the previous question that when we're repeatedly dividing by 2 like this, that's going to be logarithmic. And so we can say that there are approximately log of n over 2 levels. And for each of those levels, we have n over 2 amount of work. Right? So if we're adding n over 2, log of n over 2 times, then the entire sum is going to be equal to n over 2 times log of n over 2. Right? And writing this in big theta notation, this is going to be theta of n log n, because we drop multiplicative factors as well as lower terms. And so now we have some big theta of n squared term, and we're adding to it a big theta of n log n term. And so we know that lower order terms are going to be dropped when we're looking at asymptotics. And so our asymptotic runtime is actually dominated by this first part, this big theta of n squared part. And so if you want to know this entire sum, this is going to be equal to big theta of n squared. And that's going to be our runtime. And so once again, the question did ask for best and worst case runtime. But we'll notice that when we did our analysis, we didn't really care about the value of n, and we looked at an arbitrary n, right? So there wasn't really a need for best and worst case runtime because it actually always runs in big theta of n squared time. And so in this case, the best case is equal to the worst case once again, and both are big theta of n squared. So now we're going to move on to some true false questions. And so our first statement is if f of n is within the set O of n and g of n is within the set big O of n squared, and both functions are non-negative, then the absolute value of g of n minus f of n is within the set big omega of n. Right? And if this is true, explain why. Otherwise, give a counterexample. And so really quickly, just to review what big O and big omega are, right? You can think of big O as an upper bound. So when we say that f of n is within big O of n, it means that the order of growth is upper bounded by something, right? With the case of f of n being in big O of n, it means it's upper bounded by a linear rate of growth. And so g of n would be upper bounded by a quadratic rate of growth. Big omega is kind of the opposite, and it specifies a lower bound. So the order of growth is lower bounded by something, right? So it grows at least as fast as this, whatever our big omega is of. And so now we can actually take a look at this statement and see whether it's true or not. So in this case, we have that f of n is in big O of n, g of n is in big O of n squared. And so is it possible for their difference to be not in big omega of n? And so one thing I kind of saw immediately was, what if g of n is equal to f of n, right? In this case, g of n minus f of n is going to equal 0. And so 0 is not in big omega of n because its rate of growth is like 0 when it should have at least a rate of growth of n. And so in our case, let's see if there's any inputs or I guess examples for an f of n and g of n that actually fit this case, right? So one thing that we can say is, what if f of n is equal to n, right? Well, n is in big O of n because it's upper bounded by a rate of growth of n. And what if g of n is also equal to n? Well, this is also big O of n squared, even though it's not a tight bound, right? N squared grows faster than n, and so g of n is in big O of n squared, or the set of functions big O of n squared. And so what does g of n minus f of n look like? Well, this is going to be equal to basically 0, and 0 is not in big omega of n, and so this is a counterexample. And our answer here will be false. Now for part D, we're given the statement if f of n is within big theta of n and g of n is in big theta of n squared, and both functions are non-negative, then is g of n minus f of n in big omega of n. Right, and so in this case, what does big theta mean? Big theta just means that f of n, in this case, grows at the same rate as n, and g of n asymptotically grows at the same rate as n squared. And so just looking at this problem, we know that when we're looking at asymptotics, that as n grows really large, lower order terms become negligible, right? And so if we have g of n growing at a rate of n squared, and then f of n growing at a rate of n, then f of n becomes negligible because it has a lower order rate of growth. Okay, and so what this means is that when we look at the difference g of n minus f of n, it will be greater, or it will have a rate of growth that is at least n. In fact, it's going to have a rate of growth which is also at least n squared, right? But we know that big omega of n is a superset of big omega of n squared, and so we can say that this statement is true. Right, so now moving on to part E. Part E asks us to find the running time of the following algorithm as a function of the parameter r. And so in this case, let's take a look at the function. It's going to be a method called best, and it takes in 3 parameters, right? So the first parameter is a vals array, and this vals array just gets passed down. Right? And so what is vals? Vals is going to be a square array, and our next 2 inputs r and c are going to specify a row and column within that vals array. Right? And so the bounds on r and c are between 0 and vals.length. And so now what happens during this method? Right, during this method, we have a base case. So if r is equal to 0, then we're just going to return the value at that row and column. Otherwise, we're going to make some recursive calls, right? And so our recursive calls, once again, we have some if conditions here, but there are 3 possible recursive calls we can make. And so our first recursive call, let's say that we choose an initial r and c right here. Our first recursive call is going to be to r minus 1 and c. And so we're using this grid right here to represent the vals array, and r and c to represent like a location within that. And so r minus 1 comma c is going to represent a recursive call to this cell here. And so if c is greater than 0, looking at the next recursive call, basically if c is not within this row or this column, then we'll make a recursive call in this direction too, to r minus 1, c minus 1. Then if c is less than vals r dot length minus 1, basically if it's not in this column here, then we'll make a recursive call in this direction. And so in this case, we're making 3 recursive calls at most, and that's what this part does. And then really quickly, just for completeness, we'll see that we have some constant amount of work here, and you can write it so. And so it looks a bit complicated, especially with all of our if conditions, but let's just ignore the if conditions now and apply our 4-step process from parts A and B. Right, so the first step was to draw the recursive call tree. And so let's say that our initial inputs are to R and C. Right, I know that like vals is passed in as well, but vals doesn't change for any other recursive call. And so let's just omit it just to make things a little space efficient. Right? And so what are the recursive calls made by this call to best with inputs vals R and C? Right? Once again, we're ignoring the if conditions just for now, and we'll see like why that's possible later on. But this makes 3 recursive calls. Our 3 recursive calls are going to be to R minus 1, C minus 1, R minus 1, C, and then also R minus 1, C plus 1. And so what recursive calls do these calls make? Right, each of them also makes 3 recursive calls. And like each of these will also make 3 recursive calls and so on. As you can see, it just is a pattern, it keeps fanning out with like a branch factor of 3. And so now we can move on to our next step, which was calculating the work per node. Well, we said that there was a constant amount of work done. And so we can just say that there's like 1 unit of work for each of these nodes. And this goes on. And so now that we've completed that step, let's actually calculate the work per level. And so I'm gonna move this over here so we have a little bit more room. But what is our work per level, right? Let's call our work per level here. And remember, work per level is just calculated by summing up in this direction the amount of work done at each level. So the first level does 1 amount of work, next one does 3 amount of work, next is 9, which might be easier to think about as 3 squared, and so on. Right? And so what is the lowest level of our recursive call tree going to, or what amount of work does our lowest level of our recursive call tree perform? There's a branch factor of 3 for every single level, and each of our nodes here still performs 1 unit of work. And so if we have 1 row corresponding to 1 level, right? So this is like row R, this is row R minus 1. Our lowest level will correspond to R is equal to 0. Right? And so there's going to be R levels in our recursive call tree. And so the lowest level will have 3 to the R work. And so in this case, now let's actually calculate the sum, which is our step 4. Our sum is going to be 1 plus 3 squared plus 3 to the R. And you should notice that this is a geometric sum, sometimes called a dominating sum as well. And you should know that the dominating sum is called the dominating sum because it's dominated by the largest term, in this case 3 to the R. And so this sum is going to be big theta of 3 to the R. Right? Another way to think about this is that it's a geometric series. And if you calculate what the value of the geometric series is, you'll find that it's also a big theta of 3 to the R. But it's just a good sum to know. And so that's going to be our answer, which is big theta of 3 to the R. But one thing we neglected to talk about up to now is all of these if conditions, right? And so let's take a look at what these if conditions mean. So the if condition, the first one is if C is greater than 0, then we perform the recursive call. So when is the case that we don't perform that recursive call? Right, that's going to be when we have C being in this last column here, or this first column. And so in this case, we'd only make 2 recursive calls, right? The one to R minus 1 comma C, and then the one to R minus 1 comma C plus 1. Similarly, on the other side, we would only make this recursive call here if we're not in this last row. But if we're in the last row, then we'd only make 2 recursive calls. And so this seems to complicate things a little bit, right? Because sometimes we aren't actually having 3 recursive calls for all of these nodes. But why is it the case that we can kind of neglect that? This won't be a very rigorous argument, but one way to intuitively think about it is that when we're looking at asymptotics, we are considering n that is very large, right? And so in this case, n is going to be the length and width of our vals grid. And so if n is very large, then 2 of these cells out of the entire n of them does not have much impact on the overall result, right? And so another way to think about this more mathematically maybe is that if we have n columns, then n minus 2 of them will have a branch factor of 3. And then 2 of them will branch by 2. Right, so this is the one, these are the ones that branch by 2, and then all the other n minus 2 columns will branch by 3. And so looking at this entire level, what is the branching factor? It's going to be approximately 3 times n minus 2 plus 2 times 2, right? Which gives us 3n minus 4. And so one way to interpret this is that the branching factor is going to be, or sorry, this should be minus 2. Well, one way to interpret this is that the branching factor is still approximately 3 times the number of columns, right? Because in this case, n is going to be very large, and so the minus 2 here doesn't really matter that much. And so that's like an intuitive definition or intuitive explanation for why we can disregard the edge cases for when we're at this column or this column, and just say that it's still going to be big theta of 3 to the r. Now let's take a look at part F. And so with part F, it says that suppose a function from part E is now memoized. And we want to now give an expression E that involves the parameters r and n, such that the running time of the memoized function is big theta of our expression. And so let's start by talking just about memoization and like why it's important, what it's used for, and then also how to calculate its runtime. Right. So when it comes to memoization, the idea behind memoization is that we want to reduce the number of repeated computation we're doing. But because some computation is expensive, and if we want to redo it multiple times, why not instead just compute it once, save the result, and then we can use that value later on. Right. And so let's try to contextualize this a little bit by taking a look at our best function. Right. Let's say that our initial input is going to be here with this value of r and c. Right. It makes 3 recursive calls. It's going to make a recursive call here, recursive call there, and a recursive call there. Each of these are also going to make 3 recursive calls. It's going to look like this, this, and this, these, and then these. And you'll notice already that there's a lot of overlap in some of the inputs that we're passing into best, right? For example, we're calling best 3 times for this value of r and c. And so this seems wasteful already, right? Because the amount of computation we have to do in order to compute this input here, or best called on that input, includes a lot of the recursion that starts from this point onwards. And so if we have to redo that computation multiple times, it's going to get pretty expensive pretty quick. So this is where memoization comes in, right? What if instead, the first time we see this input, we try to compute it. But from that point onwards, once we get the result, why don't we instead just save the result so that we can use it in the future? Right? We call this caching. And so we'll store it in a cache, and we can retrieve it in constant time whenever we need it in the future, instead of having to redo the expensive computation. And so that's the general idea behind memoization. So now let's talk about how to actually calculate the runtime. And so when it comes to memoized functions, the way we'll calculate the runtime is now basically with a 2-step process. The first step is going to be to count the number of different inputs we are trying to compute. And then next, we want to calculate the work done to calculate or to compute each of those inputs. right? And so what does this mean for our method best? Once again, let's say that our initial R and C are somewhere here. And so let's do step one, right? So step one says count the number of different inputs to the function. And so we know that based on our recursion, we're going to have to calculate best on all of these inputs here, right? Like all of these, then branches by 3. And when those branch by 3, we're going to have to calculate these inputs and so on. Right. And so everything highlighted in blue, it includes like an input that we have to calculate. And so now how much work is being done to compute each of those inputs? If we take a look at our best method up here, we have to do this amount of work. Well, we define this double variable, and then we possibly make some amount of recursive calls. And so when calculating this amount of work, we don't include any of the recursive calls. We're just calculating the work for that specific node. Right? And so in this case, if we're making constant work plus some constant number of recursive calls, then our work is going to be constant. Right? And so when trying to calculate the runtime of our method best, when it's memwise, we can just basically count the number of different inputs and then multiply by a constant. And so that's the approach we're going to take. And so the answer that the solutions give is going to be theta of r times n. And so there's actually a slight mistake with the answer given, and we'll see why in just a little bit. Let's talk about how they got r times n. Right? And to do this, we're going to start by trying to upper bound the runtime of this memwise function. And so we said that we can basically just count the number of different inputs to the function that we ever have to compute, right? And that's going to be everything shaded in blue. But we can see that we can upper bound this by taking a look at this rectangle here, right? Because this rectangle here includes everything in blue with some additional inputs that we actually never calculate, but are nice to have, right? And so in this case, what's the size of this rectangle? Well, there's going to be, let's see, r values in this direction, right? So you can think of this as like a height of r and a length of n. And so if we have a rectangle with side length r and n, then the total number of cells and basically the total number of inputs that we ever have to calculate is upper bounded by this O of r times n. We'll see that that's actually not going to be tight enough to be a theta bound. And to do that, let's take a look at a different set of inputs, specifically when r is equal to root n and c is equal to n over 2. And so when this is the case, I've already drawn it out here, but this will correspond to the initial input right here. Right? We'll see that r and c still asymptotically grow with n and become larger and larger. But how many cells are we shading in? Right? We're shading in like all of these cells, and it looks like a triangle. So we can approximate it with our triangle formula, just 1/2 base times height. And so what is the base? The base is going to be around r in this direction and r in this direction, right? So we can approximate the base as 2 times r. We can approximate the height as just r, right? Because that's actually the number of rows being the height. And so in this case, the total number of cells that we're shading in is going to be around 1/2 r times 2r, which is equal to r squared. And so why is this not the same as a runtime of big theta of r times n, right? We said that r squared, or we said that r is equal to root n, right? And so r squared is going to be root n squared, which is just n. On the other hand, r times n, when r is equal to root n, is going to be root n times n, which is not the same thing as just n. And so in this case, a more accurate answer to this solution would this be using big O of E instead of big theta of E, because of this counterexample we saw here. So that was all of this question covering asymptotics. Hope you enjoyed.